Okay, here we go. So this is problem 423 in the textbook. One of your homework problems. So let's start out simply. Let's find the reaction. So I'll assume that was point B. So I'll call that BY. And this was point A. Call that AY. So let's quick. Yes?
I think last time, some problem you were going right to the shear instead of the reactions.
Yeah, I don't know the shears. I don't know the reactions right off the top of my head.
I tried it that way. That's what gave me the problem.
Oh.
If I do it like you're doing now, I'm good.
Yeah, I could probably guess what they are, but I don't think I can do it right off the top of my head on this one. Yeah, some of the simpler ones I just know what they are because I've done them so many times, or there's just the one simple reaction. But this one, if you go ahead and sum the moments, I'll sum the moments about A. All my applied forces will then be negative, and BY will create positive. So I'll do all my negative ones first. So I have 500 pounds, and that's times 8 feet. Then 200 pounds, and that's 16 feet. And then 300 pounds, and that has a moment arm of 24 feet. And then BY creates positive moment at 16. So BY will be, what will BY be? Looks like 900? That makes sense? Anybody else get that? 900 pounds sound familiar? Oh, you're working on it?
Yes.
Okay. So then we can sum forces in the y direction, and we'll have AY and BY acting up, and then all these other forces, 500, 200, and 300 acting down. And that's what? That's 1,000. So it looks like AY is 100. That sound familiar? Yeah.
This is one of my questions. The moment about A.
Mm-hmm.
Why would the 300-pound force cause a moment about A when it's broken up by the supported B? That's what.
Well, you don't even look at it, right? You just look at the individual forces. So about A, each of these forces is creating a clockwise moment.
But
which
common
is
sense-wise,
there's no common sense here. It's statics,
Copy that.
right? This is not common sense to me. I did not grow up, and my parents did not instill in me equilibrium about a point.
I was thinking
It was something I had to learn.
torque on, like leverage, torque on is what I'm moment.
That's exactly what's happening, right? So what you do is you just take each one as it's happening individually. Don't look at the group. The equation will take care of the net effect. Just process each force individually and let the equation tell you what the result should be. Obviously, as the reaction moves in and out, your idea of a lever arm would be true. So as you go in, you would have to have more force, and as you went out, you would have to have less force. And that's true. So it is using a lever arm, force times distance on each one, but it's the net effect of all of them.
So B would stop 300.
I'm sorry?
So that's what I was saying was 300 wouldn't cause a moment about A because BY is sitting there.
It's an equilibrium, right? So there is no movement at all.
Okay.
Right?
Yeah.
But if you look at how each one would potentially rotate, but the trick here is that you're balancing and you're saying that the sum is 0. A lot of that's something we say every class, but it's a pretty powerful statement when you think about it. We're saying that, all the moments on this object need to be equal to 0, which means there is no movement. If it was not balanced, if this was not equal to 0, then our beam might be up there spinning around forever. Again, that's not a good situation if you're trying to build a bridge and trying to drive on it and it is moving. Unless it's an amusement park ride, that could be kind of interesting. Okay, so once we have those, and I think they're reasonable, I'll go ahead and draw my template for the outs from left to right of the beam, and I'll go ahead and say for my shear diagram, here's my positive X. I'll assume shear is positive, and all my values will have units of pounds. We also know that at these applied points are going to be transitions in our shear diagram, so I'll go ahead and include those in my template. Now don't forget our basic rules that the change in shear is the area under the load diagram, and then of course we have the differential version of that, which is the derivative of the shear diagram is equal to the load. So these are the two things that we're going to use to always build our shear diagram. So starting on the left, what's our shear look like? What's AY is positive, it's 100 up. What kind of shear is that? Up on the left side. That's positive. So we're going to start at what? A value of 100. Positive shear of 100. Now the change in shear over the first 8 feet is the area under the load, and the area under the load is 0. So it's going to stay 100. And then the shape of the shear diagram is equal to the load. What's the value of the load over the first 8 feet? 0, so that means the slope is 0. 0 slope is a horizontal line. Now what happens is you go from the left side to the right side and you pass under that 500-pound force. Well, the change in shear is equal to that load. So you're going to go from 100, you're going to drop down 500, which will bring us to negative 400. Okay? Now what happens over the next 8 feet? Well, the change in shear is the area under the load diagram, which is 0. So we stay at 400. What's the slope? What's equal to the load? What's the value of the load? 0. 0 slope. So we've got constant shear to this point. Now what happens is we hit BY. BY is 900 up. So 400 minus 400 plus 900 brings us to 500. But we also have the 200 pushing us down, which brings us to 300. Same thing as the first two sections. The third section says the change in shear is the area under the load. Area under the load curve is 0. So we stay at 300. The slope of the curve is the load. The load is 0. So there we go. There's your shear diagram. Well, it ends up being positive 300 shear. Does that work? In case you forget, if you drew a little free body diagram of just a little sliver of the beam on the right-hand side, a little DX sliver, where the applied load of 300 pounds, and you're approaching it just from the left, well, positive shear on that face is up. And you can see through equilibrium, they balance. So you should have a positive 300-pound shear. And you do. A lot of people say, oh, shear goes back to 0. No, shear does not go back to 0. The shear is positive 300. So where's the maximum shear in the beam? Minus 400. And it occurs in the middle third. Okay? So now it's time for the moment diagram. So I'll draw my positive X and my positive moment. The units will be pounds for force and feet for distance. Do I know something about the moment? Well, I know the moment at A. It's a external roller, so I know that's 0. Now, an internal support, the moment at the support is not necessarily 0, and probably is usually not 0. But we know something about the free end. It's 0. So I know where I'm starting, and I know where I'm going. Okay? So we're going to use the rules now for the moment diagram. The change in moment is now the integral under the what? Shear diagram. And the change in the moment with respect to x, the derivative of the moment diagram, is the shear. So these will be the set that we'll use for this diagram. So what's the change in moment over the first 8 feet? I'm starting at 0. According to this, it's the area of the shear diagram, which is what? 800. So 0 plus 800 is 800. The slope of the moment diagram is equal to the shear. What's the shear over the first 8 feet? It's constant and positive. So here's a constant positive slope. In fact, if you actually looked at it, it would be positive 100 to 1 for the slope. Now the change in moment over the next 8 feet is the area in the shear diagram. What's the area in the shear diagram here? Well, it's a rectangle, so it's minus 400 times 8, which is negative 3,200, right? 800 minus 3,200 is what? 20, what did I say? 32, 24? So that's minus 2,400. What's the slope? Well, if you look up here, the slope is constant and it's negative. So here's a constant negative slope. In fact, if we marked it off, it would be minus 400 to 1. Now the change in moment is the area under the shear diagram here, the last 8 feet, which is 3 times 8, which is positive 2,400. This is a positive area. This is a negative area. This is a positive area. So, of course, negative 2,400 plus 2,400 gets us back to 0. Yay! And the slope is equal to the moment. The shear. The shear is constant, positive. Here's a constant positive slope. This is not to scale, obviously, but it would be a 300 to 1 slope. And there's your moment diagram. So where's the maximum moment? It's 2,400 and occurs over the support at B. Mr. Abney.
In the shear diagram, why did you go from negative 400 to 300?
Well, I started at negative 400, right?
Right.
And then the first thing I encounter would be my reaction, which means I go negative 400 plus 900. That brings me up to positive 500. And then I have the 200 push me back down to, or you could take the sum here. 900 up, 200 down, that's really 700 up. So negative 400 plus 700 brings you to 300. The other good thing too here is that it needs to match the shear you would expect out here at the free end, like we talked about over here. So any other questions about that one? Okay.